Hello everybody, my name is Christian from Master of Digital and welcome to this mini course called Machine Learning in Construction. Note, this course has been made in collaboration with Data-Driven Construction. Machine learning is the process of enabling computers to program themselves. If programming is automation, then machine learning is automating the process of automation. Let's start by understanding the basic terms used in machine learning. Labels. A label is the value we aim to predict, essentially the y variable in a simple linear regression. Labels can represent a wide variety of parameters, such as the number of days to complete a task, the cost of goods or services, or other key outputs. In our construction example, labels include the cost and duration of work. Features. Features are individual independent variables that act as inputs to the system. Prediction models use features to make predictions. Each column in a dataset can be considered one feature. These are sometimes called also attributes. The total number of features is referred to as the model's dimensions. In our example, features include various building parameters such as the number of floors, the number of apartments, and the width of buildings. Model. A model is a family of hypotheses, one of which we hope closely approximates the target function. Algorithm. A machine learning algorithm identifies the hypothesis within the model that best satisfies the objective function. Training set. During training, we pass an algorithm the training data, which helps it learn patterns. The algorithm identifies patterns in the training data, aligning input parameters with the desired output. The result of this process is a trained machine learning model that can be used for predictions. This process is also known as learning. There are three major types of learning: supervised, unsupervised, and reinforcement learning. Supervised learning. In supervised learning, an AI system is provided with labeled data, meaning each data point is tagged with its correct label. The system's goal is to approximate a mapping function so well that when given new input data or x, it can predict the corresponding output variable or y. Unsupervised learning. Here, the AI system is given unlabeled, uncategorized data. The system's algorithms process the data without prior learning, and the results depend entirely on the coded algorithms. Reinforcement learning. In reinforcement learning, an agent learns by interacting with its environment. It receives rewards for correct actions and penalties for incorrect ones, mimicking human learning. For example, think of a child learning to read. The process doesn't start with memorizing grammar rules. The child begins with simple books and progressively moves to more complex ones, gaining knowledge, understanding the rules along the way. Machine learning works similarly. Let's consider an example: predicting house prices. A traditional algorithm would require explicit rules based on features like house size, land area, number of rooms, and location. However, this approach assumes we know the exact formula to compute the price, which isn't always practical. In practice, we often don't know the precise formula. Instead, we can use a machine learning algorithm that builds a model based on limited knowledge. The model is refined by training it on examples of housing prices, combining the initial model with data to improve its predictions. In our example, the machine learning model, we use partial knowledge of housing pricing rules and refine it with data from real projects. The algorithm takes input features and expected output values from training datasets to create a predictive model. For example, we could use cost and duration data from similar buildings to train a model. This trained model can then predict outcomes for new projects. Supervised learning is similar to a teacher guiding a student. The algorithm is adjusted based on its performance, learning iteratively until it reaches a satisfactory level of accuracy. Let's revisit the construction example to see how predictions work in practice. From old project data, we collect parameters like width, height, total area, and other key construction metrics. Let's simplify this with 3 sample projects, each with 3 parameters: number of apartments, number of floors, and a complexity score. For instance, project 1 has 5 apartments, 7 floors, and a complexity score 2 out of 10. This project took 270 days to complete and cost $4.5 million. Now we want to predict the time and cost for a new project with 4 apartments, 4 floors, and a high complexity. One approach involves the k-nearest neighbors algorithm. Here, each project is represented as a vector in a multidimensional space based on its parameters. With 3 parameters, we can visualize projects as points in 3D space. For a new project X, we calculate the distance to existing projects and identify the nearest neighbors. This helps us determine average values for cost and time based on similar past projects. This method is an example of KNN, k-nearest neighbors, a supervised learning algorithm used for both classification and regression tasks. To implement KNN, we first load training and test datasets. Next, we choose K, the number of nearest neighbors to consider. For each test data point, we calculate distances to all training points, sort them, and choose the top K closest points. In our construction example, this approach predicts that the new project will cost approximately $3.8 million and take 250 days to complete. In the next session, we'll explore real-world application of these methods using actual datasets to predict construction costs and timelines.